Every polynomial has a specific value depending on what you plug in for x. A 0 is simply the exact x value that makes the entire polynomial's value drop to exactly 0. This series of graphs shows what that looks like on a coordinate plane. If you look closely at graphs 2, 3, and 4, you'll see the curve intersecting the horizontal x-axis. At those exact intersection points, the y value is completely zeroed out. Looking at a graph is helpful to see approximately where these zeros live, but to find their precise numerical values, we have to rely on algebra. We need a reliable method that doesn't require plotting points on a grid. That method is the factoring workflow. We start with the standard quadratic equation, ax squared plus bx plus c. Let's map this to a real example, x squared minus 2x minus 8. To split the middle term, we need two numbers that multiply to our constant, negative 8, and add up to our middle coefficient, negative 2. After testing the factors, negative 4 and positive 2 are the only numbers that fit both rules. We use those two numbers to rewrite the equation, expanding it into two binomial factors. Now we have the quantity x minus 4 times the quantity x plus 2, all equal to 0. Because the product is 0, one of these factors must be 0. We set each parentheses equal to 0 independently, which gives us two answers, x equals 4 and x equals negative 2. If you plug either 4 or negative 2 back into the original expression, the entire calculation zeroes out perfectly. These two solutions, 4 and negative 2, are our verified zeros. We will keep these numbers handy to test the integrity of the quadratic verification formulas. To guarantee our factoring is correct, we use two verification rules. The sum of the zeros, alpha plus beta, must equal negative b over a, and the product of the zeros, alpha times beta, must equal c over a. Let's test our zeros. First, we add 4 and negative 2 to get a sum of 2. Then we multiply 4 and negative 2 to get a product of negative 8. Now we check the coefficients from our original equation, x squared minus 2x minus 8. Here a is 1, b is negative 2, and c is negative 8. Let's plug these into our formulas. Notice what happens with the sum formula. We need negative b over a. Since our b is already negative 2, we get minus a negative 2. Those two negatives cancel out to give us a positive 2 over 1. The values perfectly match the sum and product we calculated directly. These formulas act as a mathematical mirror. If both sides don't reflect the exact same number, you know there is a flaw in the original factoring logic. Let's try an equation with a missing linear term, t squared minus 15 equals 0. We can solve this directly by moving the 15 to the other side and taking the square root. Since a negative number squared also produces a positive, we must include the plus or minus symbol. This gives us our two zeros, positive root 15 and negative root 15. Next, we need our a, b, and c values for verification. It's common to accidentally label the negative 15 as the b term, but b is always the coefficient attached to the single variable. Because there is no single t term in this polynomial, b is simply 0. The full expression is actually 1t squared plus 0t minus 15. Recognizing that hidden 0 is the only way to pass the verification check. When we add our zeros together, positive root 15 plus negative root 15, they cancel out to 0, which matches our negative b over a perfectly. Let's step up the complexity with a leading coefficient greater than 1, 3x squared minus x minus 4. Here we must multiply the a and c terms first. 3 times negative 4 gives us a target number of negative 12. Using that target, we split the middle term and factor by grouping. This gives us the factors 3x minus 4 and x plus 1. Setting these to 0 gives us our solutions, a fraction, 4/3, and negative 1. To verify, we add 4/3 and negative 1, which leaves us with 1/3. Checking our negative b over a formula, we get minus negative 1 over 3, also exactly